The question is, could you do an example on the calculation of bending stress in a beam? In this example, I will consider a symmetric I-beam. This is the problem that I have chosen here. We have a simply supported beam subjected to a triangular distributed load. The shear force and the bending moment diagram for the problem are given. The beam is an I-beam with this cross-section. The questions are, number one, to determine the maximum tensile and compressive bending stresses in the beam, and number two, the fraction of the bending moment carried by the flanges. I call this a symmetric I-beam because the cross-section is not only symmetric about the y-axis, but also symmetric about the z-axis. And here, the y-axis is a vertical line that runs through the center of the cross-section, and the z-axis is a horizontal line that runs through the center of the cross-section. Because the two flanges are identical, you can see that the cross-section is symmetric about the y-axis as well as the z-axis. And if you recall, the centroid of a cross-section lies on lines of symmetry. There are ones, right? On that basis, we know the centroid must lie on the y-axis, it must also lie on the z-axis, and therefore it lies right at point C, which is the intersection of these two axes. One of the steps in solving problems like this is to find the location of the centroid. So that task is trivially achieved here. We already know this is the centroid, right? Alright, so having said that, let's come back to the problem here. We are supposed to calculate the maximum bending stresses, right? The maximum stresses go with the maximum bending moment in the beam, and by looking at this bending moment diagram, we see that the maximum bending moment in the beam is 32.7 kilonewton meter. And of course that happens at a point over here which is at a distance of 2.45 meters from point A. And we also note that this value is a positive value, right? So let's go ahead and list the value here and take it to the next slide and do the calculations. Let's try to understand this problem a little bit within the framework of the theory of bending stresses. We noted in the earlier slide that the maximum bending stress is a positive quantity, right? If you recall the sign convention, this is the positive direction for the bending moment, right? A positive bending moment acts counterclockwise on the free body diagram on the left side, like shown here, right? So if I were to take a small segment of the beam at point D, where the maximum occurs, and draw the direction for the bending moment, this is the correct direction, right? On this basis, you can see that the bending stress is compressive above the neutral axis and tensile below the neutral axis. In other words, in this part right here, we have tensile stresses, and this part right there, we have compressive stresses. And of course, the neutral axis is the axis that passes through the centroid, right? So here the z-axis is the neutral axis. Furthermore, our bending theory told us that the bending stress varies linearly with y. It is 0 on the neutral axis. So for this problem, we have the maximum compressive stress at the top of the beam and maximum tensile stress at the bottom of the beam, right? The flexure formula, which is this, allows us to calculate the values of these stresses, right? Taking tensile stress as positive, the maximum compressive stress then will be minus mc over izz, where m is the bending moment on this cross section, and of course we're going to be using m max for that. C is this distance, which for this I-beam would be half the depth of the cross section. Izz is the second moment of inertia about the z-axis, right? The tensile stress, which occurs over here, has the same magnitude, but it has a positive sign. We also know that because the beam is symmetric about the y-axis, the bending stress only depends on y. It does not depend on z. In other words, I can take any point on that line right there, for example, like point A and point D. The bending stress will be the same at both of these points. To answer the second question, which is to calculate the fraction of the bending moment carried by the flanges, what we do is we calculate the bending moment just due to the bending stresses within the flanges. Alright, so with this understanding, let's go ahead and do some calculations here. The first thing we need to do here is to calculate a value for the second moment of inertia, IZZ. Here are my calculations for IZZ. This falls within a different topic, and we did cover this comprehensively in that topic, so I won't spend too much time here. Just to point out a few key things here, we are following the approach for a composite section here. We take this I-beam, split this into three rectangles, 1, 2, and 3, but 3 happens to be identical to 1. We use the parallel axis theorem to find the second moment of inertia of this composite section. The formula for calculating the second moment of inertia about the centroidal axis for a rectangular beam is this. Now you should be able to follow this very easily. So we get a value of 0.785 times 10 to the minus 3 meter to the power of 4 for IZZ. Let's go ahead and answer the first part of the question, which is to calculate the maximum bending stresses. And we're going to use this flexure formula for that. We already have values for each of the three parameters that appear in the flexure formula. So let's go ahead and substitute the numbers for these parameters and calculate the magnitude of the stress first. Here are the details of the calculations, and I'll let you follow. So our conclusion is that the maximum compressive bending stress is equal to the maximum tensile bending stress in magnitude, and the magnitude is 8.33 megapascal. Now let's work on the second part of the question, which is to find the fraction of the bending moment carried by the flanges, right? So why don't we take this top flange and see how much of the bending moment is carried by that flange. The stress at point A is what we just calculated, right, which is 8.33 megapascal. Now I want to go ahead and calculate the stress at point E. For that, I come over here to the stress distribution diagram, and I see this is the value of the stress at point E, right? I can either calculate this value starting from scratch using this flexure formula, or I could simply use similar triangles to come up with the value here. So that's what I did over here. We see this triangle and this triangle are similar, right? And therefore, sigma A, which is the stress over here, divided by this distance, which is 0.2 meters, must be equal to sigma E, which is this quantity right there, divided by 0.15 meters. So that's what I have over here. So that gives me a value of 6.25 megapascal for the stress at point E. Now I'm going to go ahead and calculate an average stress within the flange. Alright, so I'm going to take this value, sum up the two, divide that by 2, and come up with an average value, which is 7.3 megapascal. If I take that average value, multiply that by the cross-sectional area of the flange, I'm going to come up with the force, right? So that's the force carried by the flange. Here are the details of the calculation. I get a value of 0.073 meganewton for that. The location of this force F is not going to be exactly in the middle of the flange. This is because what we have here is a trapezoidal distribution, right? This is not a uniform distribution, right? So F is going to be a little above the center of the flange. But because the thickness of the flange is so small compared to the overall depth of the beam, we can make the approximation that F acts in the middle of the flange. So if we make that approximation, C1 would be 150 plus another 25 over here, right? So it will be 175 millimeters. Now if I take this force F, multiply that by C1, that is the moment carried by the flange. So here are the details of that calculation, and we end up having 12.8 kilonewton meter for that. Now what we have calculated so far is the moment due to this compressive force, right? So this moment goes in the counterclockwise direction, right? F multiplied by C1. And similarly, there's a tensile force in the bottom flange, right? And therefore the direction of the force is this way, going to the right, and F multiplied by C1 again will be another counterclockwise moment. If we add the 2, that will be the total moment carried by both flanges. That will be F multiplied by 2C1, right? Or 2 times the M flange, the moment that we just calculated, right? So the total moment carried by the flanges would be 2 times 12.8. The actual moment acting on the cross-section is 32.7, and therefore the ratio between the two is 0.78. In other words, 78%. In other words, almost 80% of the applied moment on that cross-section is carried by the flanges. Now you see the role of flanges of an I-beam. Flanges carry the bending moment, and the web carries the shear force, as we will see in another topic.